SwayamPrabha. Digital India. Educated India.
Hello, dear friends. Now, today we will be discussing on one of the important flight phase of airplane, the cruise. When I say cruise, the airplane will be going in a straight line like this, and it will be unaccelerated. All the forces and moments will be balanced, and wings level, that is, the wings will not have any orientation like this, it will be straight and level. And this is a straight flight, that is typically a cruise flight. And when I say the unaccelerated flight, we mean that the net forces are balanced. And what are the forces acting on it? The forces acting are, one is lift force, then drag, then the thrust, and the weight. Whole performance exercise, understanding the performance of airplane, is focused towards these four forces: lift, drag, thrust, and weight. If I now come back to this diagram, if really this aircraft is going in an unaccelerated flight, then I can write thrust equal to drag and lift equal to weight. Let us also remember one thing. A designer will design an aircraft, but who will be flying it? A human being, a pilot. And the pilot may not be an engineer, may not be a person who understands lift, drag, and all the theories that has gone into designing an airplane. So it's the role of the designer to ensure that he develops a language which pilot can understand, right? And mostly this is done through instrumentation. We'll be unfolding this understanding step by step. Let us come back to first on this force balance, which is thrust equal to drag and lift equal to weight. If I take the second equation, right, the lift is, we know by now, lift is half rho v square SCL. So I can write V is equal to under root 2 W by S by rho CL, because the lift is half rho V square SCL, which is equal to the weight, as per the equation number 2. So let us focus on this equation. The two very important parameters here, one is CL, and that is W by S, and W by S we will be referring very frequently as wing loading. This W by S is wing loading. Let us develop some feel for this wing loading. Suppose we want to lift this mass m by giving a forward velocity. By now we have understood that I can generate a lift using a wing, a fixed wing. So I translate this to a diagram like this, where I call this part wing. And let us say for a given weight of airplane, the area is S, is the area of the wing, then the ratio W by S is called wing loading. What is the physical significance of it? What is our aim? Our aim is to lift the airplane. Lift the airplane how? By generating lift through the wing, primarily from the wing. So if the wing area is large, then I will be able to produce more lift. You can come here, this equation, half rho V square S, more area means I will be able to produce lift for a given velocity, if area is more, I will have more lift. So in a sense, if I now translate to W by S, which is wing loading, if S is large, it will have more lifting characteristics, it will produce more lift, so the wing loading will be less. So W by S less means produce more lift for a given V, rho and CL. Produce more lift for a given, yes, that's right. So what is the utility of this wing loading ratio? Think typically of a glider, right? The gliders will have a larger wing area. So if larger wing, very smaller wing, larger wing area, so smaller wing loading. I repeat, the glider will have larger wing area for a given weight, its wing loading will be less. That means the velocity required to balance lift equal to weight at a given altitude also will be less. So what is the implication of that? If velocity is less, that means your drag required, come to this equation, half rho v square s cd. If velocity is less, your drag experienced by the airplane will be less. In turn, the thrust required also will be less, and in turn, the engine size will be less, and the weight also will be less. Right? This is very, very important parameter, and we must always try to see these two equations together. Right? Okay. So that is about the wing loading, some first exposure. There is another important term, if you see in this equation, is CL. What is this CL? This is not just CL of the wing, it is CL of the whole airplane. So I will write, I'll be very clear in my mind, this is CL because of wing, this is CL because of fuselage, this is CL because of tail, and if any other components are there, there could be a canard, there could be any other surfaces. So CL is for the CL aircraft. What CL we are talking about is the CL of the whole aircraft, not just CL of the wing. That should be very, very clear in the mind. Okay. Now, there is a word of caution. When I write CL of the aircraft as CL of the wing plus CL of the fuselage plus CL of the tail, it should not give a wrong impression that CL of the wing, if I want to estimate CL of the wing, I take the wing separately and find for a given alpha, I find CL of the wing in isolation. Similarly, I find CL of the fuselage in isolation. Similarly, I find CL tail in isolation and then add it up. That will be a mistake. That is not correct. Because, see, the point is CL of the wing in isolation and CL of the wing when it is attached to the body have a different geometric conditions. For example, the moment I put this wing over this aircraft, there will be an influence of body on the wing and the wing on the body. So there will be an interference body to wing and wing to body, so the CL gets modified. Similarly, when I put a tail, if I take tail in isolation, I should be very careful that the value of CL computed in isolation will not be the exact what the airplane will be generating, because this tail will be near the vicinity of the body, fuselage, near the empennage, and there will be interference. So when I find out CL of the aircraft through a wind tunnel or through an analytical method, all these things are taken into account, and finally we say it is the CL of the whole aircraft, right? It is true that if I see the numbers, the CL of the aircraft is predominantly decided by CL of the wing, because, and that is true also because the wing has a unique role. Wing's role is to generate lift. And what is the role of tail? The role of tail is to generate moment. So lift is not that important for tail because the tail moment arm, the distance between aerodynamic center of the tail to CG of the airplane, that distance into the small force at the tail gives the moment which is required to control the airplane. Okay, now this V, when I use this equation, this V is actually V cruise. That is, what is the interpretation of this? It is the cruise velocity at a given altitude where you are maintaining lift equal to weight, right? And there is another subtle point about this V cruise. If I ask, is it really the velocity of the airplane with respect to the ground? The answer is no, because the lift depends upon the velocity, which is air relative velocity. That is meaning thereby, suppose the airplane is stationary on the ground. Suppose I have fixed it on the ground, and there is a wing, and there is a wind blowing. It is possible. There is a wind blowing. So what is the speed of the airplane with respect to the ground? It is 0. It is fixed. However, it will produce lift because there is a air relative speed. So V cruise, we should be very clear this is air relative speed. Okay, now let us go a little bit deep into this. Let us do an example. Suppose I want to reach from point A to point B, and I am flying like this. And I am assuming that there is no wind. No wind. And I also am assuming that I will be flying at a constant CL. No wind and at constant CL. So let us say for this configuration the velocity is V1, or I say V1, no wind. What will happen if suddenly similar situation, everything remaining same, and suddenly there is a headwind blowing like this, say wind, and still I want to fly at this constant CL. Okay? To maintain lift equal to weight, my question is, should I increase the speed or decrease the speed? The answer is obvious, because the lift depends upon the air relative speed. Since the wind is coming towards the airplane, the air relative speed will increase. So actually I have to reduce the speed with respect to the ground. So as V wind increases, V relative, right? So I need to reduce ground related speed. This is ground related speed, okay? So that the air relative speed remains same as in the first case, and lift is equally balanced with the weight. Otherwise, the airplane will lift up, right? So this concept will be used. You will see that when we are moving an airplane into the wind, or there's a tailwind, how the overall performance of the airplane will change, sometimes to advantage, sometimes to disadvantage. So with this understanding, let us come back to the cruise. We say thrust equal to drag and lift equal to weight. So I can manipulate this equation and write thrust equal to W by L by D, or this is W by CL by CD. What is this thrust? This thrust is thrust required. This is thrust required. Required for what? This is the thrust required for ensuring it is equal to the drag, and there is a sufficient appropriate value of CL at that given speed which maintains lift equal to the weight, right? What is our aim? Our aim should be, I should fly the machine in such a way that thrust required is always minimum, right? Most of the time in the cruise, we'll try to look for thrust required minimum. So I will look for thrust required minimum. And if I see here, what does it mean? It means for a given weight, CL by CD should be maximum, right? It means for a given weight, CL by CD should be maximum, right? Now, what is the meaning of CL by CD to be maximum? That also we should now ask ourselves. What is the meaning of CL by CD maximum? Or I put the question differently. I want the pilot to fly the machine so that thrust required is minimum, and this thrust required minimum will be compensated by thrust available, which comes through the engine. So if thrust required is minimum, then thrust to be delivered by the engine is also minimum. That is an efficient way of flying. But if you tell the pilot, please fly the machine such that CL by CD is maximum, pilot will not understand what is the meaning of this. So let us try to decode this information. What is the meaning of CL by CD maximum for a pilot? Okay. So we have to go back to the drag polar. A typical drag polar form, CD equal to CD naught plus KCL square for low speed, almost, let's say 100 meter per second, less than 0.3, and smooth surface. Mostly you'll find this will be almost an exact representation. The question is, what is that CL? What is that CL which will ensure CL by CD is maximum? Very straightforward. This will be one of your assignment problem. You have to find out the condition through a differentiation, and you can show that the answer is CL should be equal to CD naught by K, where K you know is roughly it is 1 by pi aspect ratio into E. So what is the message? Message is, if we want to fly at thrust required minimum, then I need to fly at CL by CD maximum, which means I need to fly at a fixed CL, because CD naught value is fixed. Typically value will be 0.022, 0.023, K for a given aspect ratio K is fixed. So CL is fixed. So what is the message? Message to pilot is, message is, if want to fly at thrust required minimum, then fly at CL by CD maximum, and that is fly at CL is equal to CL fixed, which is given by CD naught by K. So for a different airplane, this value will be different, because you know The K is 1 by pi aspect ratio E. So depending upon aspect ratio, depending upon the wing layout, the value of E will change, aspect ratio will change, then CD naught also will change depending upon what is the geometric contour, what are the protrusions, what are the profile of the wing. So for a different airplane, this value CL fixed will change. However, if you want to fly at thrust required minimum, where your engine will be giving minimum thrust, which I call thrust available, I need to fly at a fixed CL, which is CD naught by K. Let's say this value is around 0.2. Let us say. So what is the meaning? Suppose you are telling pilot, you cruise here, please cruise such that thrust required is minimum. If that is the statement you have given, or a designer has given to the pilot, it means he has to fly at CL equal to CD naught by K. Again, pilot will not be comfortable if he wants to calculate CD naught value and K. He is not aware of what is CD naught, what is K, mostly. So what is the way to handle the situation? See, lift equal to weight. So you know that half rho V square S CL for thrust required minimum will be equal to weight. So from here I can write V cruise will be equal to 2 W by S by rho CL for thrust required minimum. Okay. Let us see here. W is fixed. If I'm assuming that there is not much difference in the weight because of fuel consumption. S is fixed. CL thrust required minimum is fixed because it is governed by CD naught by K, which are fixed. So for a given altitude, for a given value of rho, there is again a fixed value of V cruise. So pilot will be flying around that value. If you can generate a table for him, at this altitude maintain this velocity, at this altitude maintain this velocity, and that's all the guideline for him to do the flying at thrust required minimum. And of course with the feel, he may not be recording explicit those numbers, but he has an idea. Then through instruments he ensures that he's flying at a thrust required minimum. So is this part clear? So I'll just repeat this and decode it point by point so that it goes into your mind. And always remember, whenever you are talking about an airplane, finally it will be the pilot in command will be flying this machine. He is not the designer, nor he need not be an aerospace engineer. So we need to translate all this understanding into a language which pilot should be able to easily understand. And that is what makes the difference between a good engineer and a bad engineer. So what do we say? We know that for thrust required minimum, I must fly at CL by CD maximum. That means I have to fly at a CL which is CD naught by K. That means the velocity for thrust required minimum will be nothing but 2W by S by rho into CD naught by K. So that is what the velocity for thrust required minimum should be maintained by the pilot at a given altitude. Please understand also here, this value will change depending upon the altitude. As I go higher and higher, the value of rho decreases, so this value also will change, it will increase. Right? So far we were discussing about the thrust required for cruise, right? Now we will be discussing about power required for cruise. Before I start talking about power required and thrust required, let us also understand we are talking about two types of engine. One is IC engine with propeller combination. With these engines are rated in terms of power. And another one is jet engine. These engines are rated in terms of thrust, Newton of thrust. So far we are talking about thrust required. Now we are talking about power required. And power required for what? Power required for cruise flight. Remember, power required for cruise flight is one important mission. Then power required to climb is another important mission. Similarly, thrust required for climb is another important mission. So we are only part of a segment of the whole flight envelope we are talking about, which is cruise flight, right? And the cruise is what? We know the airplane goes unaccelerated with a constant speed like this, almost in a straight line. So very simple. If I know thrust required was TR, then power required would be TR into V, force into velocity. What is this V? V is nothing but velocity required at that altitude to maintain lift equal to weight. So I can write this as W by CL by CD, which I know thrust required expression, and for V I can write 2 W by S by rho CL. So this is now my power required expression, right? So what we can see from here, this I can finally also write like this: W 1 plus half 3 by 2, then this is root 2 here. Here I write CL 3 by 2 by CD. Here again I write root rho, and somewhere this root of S also will come, so I write club it here, 2 by S. Is it okay? Let us check. W and W1 by 2 is W3 by 2, root 2 is here, and S I put it here, and CL1 and CL half CL3 by 2, CD is here, and rho, right? This simple expression tells us one thing, that for power required for any V or CL at a given altitude can be computed if I know what is the weight during the cruise, what is the CL3 by 2 by CD, and what is the density of air at that altitude. Right? Also it tells me one more information, that if I am looking for power required minimum for a given weight, given altitude, then the condition is the CL 3 by 2 by CD should be maximum. What was thrust required minimum condition? For thrust required minimum, to recall, the condition was CL by CD should be maximum, and we have demonstrated that it means I have to fly the machine at a fixed CL, which is given by CD naught by K. Similar question I will be asking here. What is that CL I should fly so that CL 3 by 2 by CD is maximum, or in turn the power required will be minimum? So that is the question we are going to address. Also, in addressing this question, we also try to see two components of power, like we had thrust required, zero lift thrust plus induced thrust. Here also we will try to see what is zero lift power and induced power, right? That is our objective. Let us go step by step. So now I do a little bit of algebra or simple expression. T into V infinity is equal to D. I don't write infinity, V into V. Many textbooks, they follow the nomenclature. For V, it is V infinity. It is called free stream velocity. That is the velocity far away from the aircraft. What is the significance of V infinity? We will be talking in as the course develops, right? But I am using V, right? So this is equal to what? Half rho V square S then CD naught plus KCL square into V, and I can write CL equal to 2 W by S by rho V square, and finally I can write an expression for power required as half rho V cube S CD naught plus 2K W square by rho SV. This is a straightforward method. You have to just plug in this expression here and do some arrangement to get this expression. What is important for us is, what is this term? This says, as the speed increases, power required also will increase as far as this term is concerned, and that is called zero lift power. Zero lift power. The physical interpretation is, if you make the airplane aerodynamically efficient, in a sense the shape is such that its parasite drag is minimal, then you have this value also less. And second one goes inversely with V. This is the induced power, which is very clear. As I am increasing the speed, the CL required is less. CL required less means drag will be less. Drag required less means your induced power also will reduce. Right? This is basically coming from the CL requirement. Okay? As CL reduces, your induced drag reduces, so induced power also go on reducing with speed. So if I now plot this, this is the induced power, and this is the zero lift power, and you'll find that net power will be something like this. And this is the point where this is V for minimum power. Okay? Please note that this point is not here. This is less than this point, and I will explain this. Let us analytically find out what will be this point. But one thing we understand, for minimum power, we have seen that CL3 by 2 by CD should be maximum. What the meaning? If I want to fly at minimum power, I should fly corresponding to that CL for which this is maximum, and naturally for that CL there is a fixed velocity because it is a cruise for a given altitude. So we will now find out analytically what is that CL for which I should fly so that I get minimum power. So the question I'm asking is, what is that CL or V for which CL3 by 2 by CD is maximum, that will ensure I'm flying at power required minimum. Okay? So I will now take a derivative power required by dV will equal to 0, and that will tell me, will give me a expression which you can check. 0 is equal to 3 by 2 rho V square S CD naught minus 1 by 3 CL square by pi aspect ratio E, which implies CD naught equal to 1 by 3 K CL square. CD naught equal to 1/3 KCL square. It means CL equal to under root 3 CD naught by K. Now I have to fly the machine at a CL which is given by 3 CD naught by K to get power required minimum. Okay. What was for thrust required minimum? For thrust required minimum, CL was under root CD naught by K for thrust required minimum. Now for cruise flight, if I am having same altitude, then which case I need more velocity? That will be decided by, if I am flying at a power required minimum, my CL will be higher than CL for thrust required minimum. Since CL is higher, the velocity will be less in this case. V for power required minimum will be less than V for thrust required minimum. Right? Another interesting thing we can see from power required versus velocity graph. If I draw a tangent, then this point will correspond to V for thrust required minimum, and of course this point is V for PR minimum. Why this point for thrust required minimum? You know, the slope is PR by V, which is nothing but thrust required. And that is the minimum thrust required, okay? Okay. We'll go on drawing this slope. So from power required versus velocity graph, I can find out what is the velocity I should fly, so that thrust required is minimum, and this will correspond to CL by CD maximum. This will correspond to CL 3 by 2 by CD maximum. Okay?